Welcome to Pomodoro Joe for Sunday, June 18th, 2023. Today we're doing LeetCode problem 2328, number of increasing paths in a grid. This is a hard problem. You are given an m by n integer matrix grid, where you can move from a cell to any adjacent cell in all four directions. So that will be up, down, left, and right. Return the number of strictly increasing paths in the grid such that you can start from any cell and end in any cell. Since the answer may be very large, return it modulo 10 to the 9th plus 7. Two paths are considered different if they do not have exactly the same sequence of visited cells. All right, and then we have an example here. So it looks like we need to have strictly increasing, which means we can go from 1 to 3, but we cannot go from 1 to 1. All right. So I wonder if we can go from 1 to itself. Well, we'll find out in a second. So if you can just start at 1 and end at 1, that will be 1. If you can't, you have to go from 1 to 3, that's one option, or 1 to 3 to 4, that's two options, or just 3 to 4, that's three options, or 1 to 4, that's four options. So if we can't just go from the cell to itself, then it looks like we have four options. If we're allowed to go from the cell to itself, well then every cell is at least 1. So that's 1, 2, 3, 4. Then we can go 5 from 1 to 3. And let's see, 6 from 3 to 4. And then 7 from 1 to 3 to 4. And then 8 from 1 to 4. So this is either 4 or 8, depending on whether or not you can count the cell going to itself as a path. And it looks like the output here is 8. So you can go from a cell to itself. Okay, so every cell going to itself is at least 1. All right, then we have another one, 1 to 2. So it looks like that'll be 1, 2, and then you can go 3. All right, so that's 3. Okay, so this is going to be a little bit tricky, but let's put 25 minutes on the Pomodoro timer and we will get started. All right, so I think the trick to this one is realizing that when you have any given cell, you can just look at the surrounding cells, find out how many paths it took to get to those cells, and then you can add those paths to that current cell. How do I describe this in a better way? So a better way to think about this is, if we just grab any cell, so we'll take this 4 for example, we just look at that cell, how many paths will end at this cell? Now I don't know just by looking at this cell, but if I look to the left, right, up, and down, so in this case we just have 1 up and 1 to the left. If I look at those cells, if I knew how many paths ended at those cells, then I can add that many paths to this cell as long as that cell has a lower value. So that cell can lead to this cell. So cell 1 can lead to cell 4. That means that I can add any paths that end in cell 1 to my cell 4's paths, because we can just take that one extra step. Now, if the cell is greater, for example, if we're looking at cell 3, we cannot go from cell 4 to cell 3, so we don't get any additional paths coming from cell 4 to cell 3. But we could get paths from cell 1 to cell 3, so we're allowed to add how many paths end at this cell to the number of paths that end at cell 3. So if we do that algorithm, let's just try it here. Well, 1, we can look up, down, left, and right. There's nothing below 1, so there's only one path that ends here. So this will get a 1. Now, if we look at this cell, there's no paths that are below. There's no adjacent cells that have a lower value than this. So again, this will just get 1 because it can go from cell 1 to itself. So these both get a score of 1. Now, if I look at 3, let's see, this one can come from here. So we get 1 from here, plus the 1 of the cell itself, so there are 2 paths that can end here. We look at 4, 4 cannot lead to 3 because it's greater than, so this gets a score of 2. So far we have a 1, and a 2. Now finally we look at this 4 cell. Well, this can look here, we get a 1, it gets 1 for itself, so we have 2, that's 1, 2, and then we look at 3, you can go from 3 to 4, and this cell had a score of 2. So we had 2 for the 4 because we can get 1 here, 1 for itself, that's 2, plus 2 more for this cell, so that gets 4. So we've got 1, 2, 3, 4, 5, 6, 7, 8. And that's right. So that will be our algorithm. We'll grab a cell, we'll look at the adjacent cells, see what their paths are, and then we can add those paths to our cell as long as there is a path, a way to get from that cell to this cell, meaning that cell has a lower value than this cell. Okay, so with that, we will get started. So we'll start with a result, and we'll set it to 0 to begin with. Then we will return our result at the end. Oh, but we need to return the result modulo 10 to the 9th plus 7. So we'll have our mod value out here. So this will be 10, we can do to the 9th plus 7. So we'll do result mod the mod val. All right. Now what else do we need? So for this, I will keep I call it a working grid. It's sort of a scratch pad. It's a place where we mimic this grid, but instead of storing the values like they store in the grid, we'll be storing the number of paths that end in that cell. So we can call this like the score grid or the scratch pad. I like calling it the working grid, so it's just the place where I can store values. That way, like in my example, when I went through and I found how many paths ended here, how many paths ended here, and we had 2 paths that end here, and we had 4 paths that end here, I can store those values, the 1, 1, 2, and 4, in my working grid. All right, so let's have this working grid. And let's see the dimensions of this working grid. Well, we'll fill it with zeros to start with. We don't know how many paths end at that cell, so we'll start with 0. That's a placeholder. And let's see, I need how many of these? I need the length of grid at index 0. So that's my number of columns. And then I'll need one of those for every every row in my grid. All right. All right, I'm not going to go through that too much just because that's not super important to this particular problem. That's just a general Python thing that you should learn. Okay, so we have our working grid. Now what's next? Well, there are 2 pieces here. We want to go through every cell and add that cell's, I guess, working value to our result. And we need a function that will actually calculate that cell's value. So what do we need? I'll do the loops first. All right. So for every y or x, it doesn't really matter. For every x in range, the length of our grid at index 0. So maybe I'll do a max x and a max y out here. That'll be another helpful. Let's do that. So the maximum x will be the length of our grid 0. And we'll actually make it an index, so we subtract 1. And our max y, that will be the length of our grid, and we'll subtract 1. All right, so then out here, instead of doing length there, I can do max x, but I have to add 1 to make it go all the way through x because range is not inclusive. And then for every y in range, max y plus 1. Now we'll just get the value for this cell at this x and y, and we'll add it to our result. So result plus equals, we don't have this function yet, but I will call it cell value, or cell paths for this x and y. All right. So now we need to actually define this function, cell paths. So we're just going through every single cell. We're going to grab the number of cell paths for that cell, and we'll add it to our result. So now we do need to define this here. Cell paths, this x and y. All right, well, the first thing we'll check is, have we already got a cell path count for this x and y? So that's in our working grid. So if our working grid, now one thing that's a little bit tricky here is our y is the first index and x is the second index. So if our working grid at this yx is greater than 0, then we can just return that value. We've already found the number of paths that end at this cell. so now if we don't know the number of paths that end at the cell, we'll have to figure that out. And how do we figure that out? Well, as we mentioned, we just look up, down, left, and right for the number of paths that end at those cells. So we'll have an up, down, left, and right. So the up, let's see, our up direction, well, that will be our current x, and our y, now this is also where it gets a little bit tricky, this will be y minus 1. So this is sort of using screen space type coordinates, where 0, 0 is in the top left corner, and y increases as you go down, and x increases as you go right. So y minus 1 is actually going in the up direction, y plus 1 goes in the down direction. So y minus 1, so our up direction is x at y minus 1, but that's only if we have something that's above us, because we don't want to go outside of our bounds here. So that's if y is greater than 0. Else, we don't have an up direction. We have none. Down, very similar. We have x, but this will be y plus 1. That's only if y is less than our max y. Otherwise, we don't have a down direction to go to. We'd be outside of our bounds. All right, so we have up, down, and then we have left and right. So left, very similar. This will be x minus 1, but that's only if, x minus 1 comma y. That's only if x is greater than 0. Else we don't have a left and a right. X plus 1, y, if x is less than max x, else none. So that's our up, down, left, and right. So at this point, it's kind of a standard grid traversal. So if you don't know grid traversal, you should study that. It's another one of these tools to have in your toolbox. So we have an up, down, left, and right. And I like to put these into a direction array here. So we have directions. That'll just be up, down, left, and right. And now I can loop through all my directions. That makes it a little bit easier. So for every cell in each one of these directions, maybe I'll call this cells. So for every cell in our adjacent cells, the couple things that we need to look at. First, we need to look at their value. We only look at the cells that are below the value of this current cell, because those are the ones that can lead to this cell. So let's see, I didn't actually grab the value out here, so let's grab our value out here. So that's going to be our current grid value, not our working grid. So we're looking at the original input grid. And again, we have to do y first. All right. Now, if we don't have a cell, because this could be none, some of these variables, these up, down, left, and right, it's possible that they're none. So if we don't have a cell, then we'll just continue. Otherwise, we'll get the cell x and the cell y out of this cell, and then we'll look at that value. So cell val, I can look at it directly. Let's do that. So if our grid at this cell, so again, y first, so cy and cx. So if this grid has a lower value, then we can use this one. So if this grid's cell value, if this grid's value here is less than our value, then we can lead to this current cell. And so we want to add that cell's count to this cell. So another thing I don't have here, I need a result. Let's keep a count. I'll call it count to make it separate from our external result here. Maybe I'll do this down here. All right, so we have some count. We'll start it at 1 because, again, every cell can lead to itself, so it has a default number of paths, which is 1. Maybe I'll call this path count. There we go. That makes it easier. All right, so we have our path count. Now, if that grid cell has a lower value, then we need to add its path count to our path count. So we can say plus equals the cell paths for that cell. So this will just be cx and cy. All right. And now at the end here, we will return our path count. Now, one thing we might want to do is use the modulo inside of here, because these numbers can get really big. That might be a problem. So we could actually use the modulo here. Okay, so we go through every adjacent cell. If we have an adjacent cell with a lower value, then we will grab its path count, add it to our own path count. And the last thing we need to do, we have to update our working grid. So one thing we're doing is keeping track of all of these values, like caching them out in our working grid. So let's see, our working grid for this yx will be our result down here, or our path count. All right, so I think this should do it. Let's go through this really quick. So let's start down here. We're going to go through every cell. So for x in the range from the max or 0 to max x, and y in range from 0 to max y, we'll just grab the cell paths for that cell and add it to our result. Again, we might want to do the modulo here as well, just because our result could be getting very large. Okay, then we go to the cell paths. We broke this down into a simple problem. We have every cell, we're just going through and grabbing how many paths end in that cell. Now for every path that leads to that cell, we'll be looking at the adjacent cells, up, down, left, and right. Now for every path that ends in those cells, and if that cell has a lower value, then it can lead to our cell. Yeah, so for every cell in the adjacent cells, we'll look at that cell. If that cell is a lower value, that means it can lead to our cell, this current cell, then we can add their paths to our path count. And we do start our path count as 1 because we can definitely lead from ourself to ourself. This cell can lead to itself. All right. And then of course we store everything in our working grid so that we can just grab it quickly here if we ever call this more than once on the same cell. All right, let's just give this a shot, see how we do. And we pass. Let's see if we can pass all the tests. There are certain things we can do to speed this up, and I might want to do those in a minute. Oh, but we pass. And we do pretty well, actually. We beat 94% for runtime and 54% for memory. That is crazy good. I was not expecting that. Okay, well, maybe I don't need to make this any faster. Well, we'll jump back here really quick and just try this. So one thing we could do, we don't necessarily have to, is here we could be doing a modulo by our mod value. This might help. So when we store these as a modulo value, smaller numbers means that you can do some of these additions and they'll be a little bit easier. You could also make the mod value here as well and the mod value here as well. I don't know if it's worth it. Let's just see. Let's see if that one mod value saves us anything. If it does, then we can add the other mods. And it's exactly the same, 94.66. That really doesn't save us anything. Oh, it does save us quite a bit on memory though. We go from 54% for memory and we jump up to 79% for memory. So these mods actually do save us quite a bit of memory because we're storing smaller integers. Let's actually do that here then. All right, this should be path count plus. All right. So we're going to do our mod value here, and then we'll do the mod value here as well. All right, so this might save us a little bit. It's one extra operation, but we're working with smaller integers, so it might save us something. Basically the same, 94% for runtime, 79% for memory. It looks like we might do a little bit better. Nope, it's exactly the same. All right. Well, we could do a couple things in here. Right now we do have these none values. We could actually move these into their own conditionals so that we just do the conditionals that we need to and we don't actually have to go through all of the values if we don't have those directions. I don't think it's really worth it. We're doing really well with this solution as it is. So really quick, we'll just go over this one more time. So to solve this one, we first had to figure out our algorithm. How are we going to count all the different paths? And the clue here was to figure out that we could just look at any cell and see how many paths ended on that cell. So once we figured that out, then it was fairly straightforward to go through and just say for every cell path, basically for every cell in our entire grid, find the number of paths that end on that cell, and count them up. Then we can return our value at the end. All right, I am pretty much out of time with this one, so check this one out. Again, this is LeetCode problem 2328. It's a good one. All right, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.